Okay, so today we're going to be looking at chemical equilibria for A-level chemistry. So there's two facts you need to know about reactions at equilibrium. The first is that the forward and reverse reactions occur at equal rates at the same time, and the concentrations of reactants and products remain constant, which means the same throughout, and they might not be equal to each other, so watch out for that. And Le Chatelier's principle states that if a change occurs to a reaction at equilibrium, the position of equilibrium will shift to counteract that change, and we'll see examples of that later on. So let's look at the principle with concentration. We got this reaction. If you increase the concentration of B, the equilibrium shifts to oppose the increase. This means it will shift to the right, so more B reacts, so there's less of B overall, which reduces its concentration. And since it's going to the right, there's a greater yield of the product. And now for a different reaction, we got if the pressure increases, equilibrium will shift to oppose the increase. And you need to know that more moles of gas generate a higher pressure. So in this case, equilibrium will shift to the right because there's less moles of gas in the products. As you can see, there's two moles in the products and 3 in the reactants. And shifting it to the right will ultimately decrease the pressure to oppose the increase. And this leads to a greater yield of the product. And pressure changes only affect gas equilibria. And if there's the same number of moles in the products and reactions, then pressure has no effect on equilibrium position. So for this reaction, we're looking at temperature. If you increase the temperature, then equilibrium shifts to oppose the increase. And in this case, it will shift to the left to decrease the temperature. And we know that because the forward reaction is exothermic, since delta H is negative, so the reverse is endothermic, which will decrease the temperature. And since it's moving away from C and D, then there'll be a lower yield of C and D. Okay, so catalysts don't affect equilibrium position, but they do increase the rate of reaction, so they increase the rate of attainment of equilibrium. And in some cases, low temperatures will increase the yield, but you don't want to use a very low temperature because that will lead to a slow rate. So you use a slightly higher temperature to increase the rate. In other cases, you don't use very high temperatures because there's high energy costs and high costs of like a building to maintain the high temperature. You don't use very high pressures since they're dangerous, and the vessels you need to contain that high pressure are very expensive. So let's look at the equilibrium constant, Kc. So let's suppose we have this reaction, and Kc is given by this. The square brackets mean the concentration of X in moles per decimeter cubed, and the little letters are the powers. So let's look at a calculation. Whoops. Okay. So let's suppose we have this reaction. A plus 2B goes to C plus 4D. And this is the question. 2 moles of A reacted with 5 moles of B. And at equilibrium, 1 mole of C was present. Find Kc if the volume was 10 decimeters cubed. So for C, it increased by 1 mole. And if you look at the molar ratios, then that must mean D increased by 4 moles, since it's a 1 to 4 with C. And A must have decreased by 1 mole, and B decreased by 2 moles. So if you do the calculations, there's 1 mole of A, 3 moles of B, 1 mole of C, and 4 moles of D at equilibrium. It's basically the ice method. Then you just plug in the values. You find the expression for Kc and then plug in, and you get that. And now let's look at the units. So from the previous slide, we had Kc equals that expression here. So now for the units, you plug in moles per decimeter cubed for each concentration, and you raise it to the appropriate power. Then you can cancel stuff out. And then something to the 4 over the something to the 2, you just, that's squared. And then you expand the 2 into the inside the bracket to get moles squared decimeters to the -6. And the units of Kc will vary depending on the equation. Okay, let's look at another calculation. Got this reaction is 2x goes to y plus z. So there's 0.35 moles of y equilibrium, and the value of Kc is 10, and find the concentration of x at equilibrium. So from the equation, we know that there's also 0.35 moles of z, because there's a 1-to-1 ratio with y. We find Kc, which is that here. Then we're rearranging for x squared. So we move this to that side and bring the Kc down. Now we just sub in the numbers to get x squared, and then we square root. Now we did not use the volume here because it's not necessary to know the volume, because there's equal moles of reactants. Here there's 2, and here there's 2 in the product. So the volume will cancel out in the Kc expression, so you don't need it. And in this case, Kc has no units again, because there's equal moles, so they cancel out. Let's look at factors affecting Kc. It's not affected by concentration or pressure, since equilibrium will shift to keep the concentration and pressure constant. It's not affected by catalysts, as the rate of the forward and reverse reactions are increased by the same amount when you use the catalyst. It is only affected by temperature, as there is a new equilibrium. If a temperature change causes a higher yield, then Kc increases. But if it causes a lower yield, then Kc decreases. And so yeah, please like and subscribe.